Hello everyone. Today I'm going to talk about the image analysis with the Bayesian inference about our project. And I'm going to introduce about the introduction, why I would like to do this project, and I'm going to talk about the prior, which is called the Ising model. Then Yuting will talk about the posterior inference and our procedure for called Gibbs sampling to denoise the original image. And Xiaoyun will show you the result and conclude our results. Okay, so image can be regarded as a statistic object. So here is a question. Suppose now we have a noise image which is x, and how can we infer the true image, a clean image, y? How can we inference this conditional distribution of the clean image given the noise image? From the Bayes theorem, we know that it's sufficient to know if you have a likelihood, which is the conditional distribution of the noise image giving the true image, and if you have a prior for the true image, then it's sufficient to inference this conditional distribution. So here is the thing. Here's the thing. How can we infer the prior of the true image? The prior here we're using is called the Ising model. Before I introduce the Ising model, I'm going to talk about the Markov random fields here. The image is a 2D object. It has a lot of pixels inside. If we want to estimate the full conditional distributions over all the pixels, then that will be pretty complicated. So here, the Markov random fields just make it easier. It says that every pixel is only dependent on its neighbors. Suppose now you are having a pixel here, so it's only dependent on its 4 neighbors. If you we are independent on the pixels other than these 4 neighbors. So this is then let's talk about the Ising model. This is the representation of the Ising model. The y here is the pixel value of each of all the pixel value of all the pixels. The pixel value can be either -1 or +1. The w here is the interaction term, which represents the interaction between 2 adjacent pixels. If w is large, it means that 2 adjacent pixels will have very strong interaction. They will tend to choose the same pixel value. If w is very small, it means that the interaction is fairly weak. Then the 2 adjacent pixels, they are kind of independent on each other. So they will not. The result can be pretty random. The ZW here is called a partition function, which considers all the situation of the pixel values. It's a normalization constant, but it's also a function dependent on the W we choose. This is the conditional distribution of the pixel value giving other pixels and the parameters. The sigma here is called the sigmoid function. Okay, so here is the question. Why we choose the Ising model to model the true image? Now, so here I'm going to use the 30 times grid Ising model performance to explain why we use the Ising model. Oops, sorry. So now here we have 5 plots which are the grids after 100 iterations of the different W value in the Ising model. We can see when the W is fairly small, such as 0.1, 0.2, 0.3, the pixel distribution is kind of random, which means each pixel is kind of independent on each other. If one pixel chooses +1, its neighbor can be either +1 or -1, and they are kind of independent. But when the W is large, for example, like 0.5, then we can see the pixels having the same value, they tend to aggregate together. So if we go back to our true image, we can see the image for the pixels having the same value, they also tend to aggregate together. So this is the reason why we would like to choose the Ising model, because it can assure us that all the pixels, they will aggregate together and having the same value. This is the average value of the grids over all the pixels. As we can see, when the W is small, like 0, 0.1, 0.2, after with the iteration going on, finally all the value will go to be will converge to 0. Means that the grid, the value will be random. There should be roughly equal amount of +1 or -1 amount of +1 or -1 value pixels. But when W is high, for example like 0.5, the pixel finally they will converge. They will separate into two clusters, and the two clusters, one clusters with a value 1, the other cluster with a value -1, and their number they are unequal. That is why the mean value of the pixels is not converging to 0. And Yuting will talk about the posterior inference.
Then let's talk about the posterior inference and the Gibbs sampling. Based on the background of Ising model, we proposed our prior for the true image Y. Ray has introduced this part in detail, and then we proposed our likelihood. Here we assume given the true image Y, each pixels in the observed image X are independent. Then if we know the distribution for each pixel for the observed image, then we can multiply the distribution, get the joint distribution. Actually, there are a lot of ways to define the likelihood. We can define it as the normal distribution or other distributions. But here we simplify the model. We assume there is a linear relationship between the true image and the observed image. Then, based on the prior and the likelihood, we can derive the full conditional distribution of Y. Then we can derive the probability of yi equals 1 based on the full conditional distribution, and it turns out a sigmoid function. In our model, we set the parameter theta and the parameter omega ij as a constant. Then let's talk about the Gibbs sampling procedure. And here is our posterior full conditional distribution of yi, and we assume the parameters theta equals 0.5 and omega equals 0.3. First, we initialize the image as the J matrix where each entry is +1. Then we do 100 iterations. For each iteration, we do the iteration based on previous estimate image. And in each iteration, we update the value of each pixel one by one, which is I here. It ranges from 1 to L times D, where L times D is the dimension of the true image. Okay, and then for each pixel, to calculate the probability of yi equals 1, we need the sigma xi part and also the summation of this part. So we calculate these two parts, where theta is from the likelihood, xi is the corresponding pixel values from the observed image. Here, the summation of yj is the summation of observations of the neighbors of yi, which is yj. Based on, after we have these two numbers, we can calculate the probability of yi equals 1, and based on this probability, update the value for pixel I. Then we can update the whole image in one iteration. And then we can get 100 image after each iteration.
Okay, look at the Gibbs sampling result. So this is our initial image. Because we set up each ISO is 1, so we got this pure black image. And now, given the noisy image and the initial image, we got the first iteration of posterior image. So this is quite with the initial. And then we implement Gibbs sampling. Here it got the 5th iteration image, and this is 10th iteration result. This is the image of 20th iteration, and here is the image of 50th iteration. So from the image changed, we can conclude our model is worked. So here we did some quantitative analysis. We use MAE to evaluate the model's quality. So YI is estimate of a clean image, or we can say YI is our each pixel of the denoise image, and Y is each pixel of the clean image. And this plot, look at this plot. X-axis is iterations, Y-axis is MAE. So look at this period when the iteration is increased, while the MAE is decreased dramatically. And then when the iteration is faulty, the MAE is stable. So this image we choose the iteration is faulty. So look at the MAE result. So here is 0.625 is this MAE between the noise image and the clean image, and the 0.04 is the MAE between the denoise, here denoise image and the clean image. So look at the MAE is decreased a lot. Here is summary. So we use the Ising model to model the true image of distribution. So here we set our Ising model as a prime. This is our very important part in this project. And we propose the distribution as the noise image gives the true image. Here we set up likelihood. And then we propose the posterior of the noise image given the noise image. And we got the posterior. And we implement the Gibbs sampling to denoise image and reduce the mean absolute error from 0.625 to 0.304. So in this project, we use the phase parameter. Look at here. Theta is 0.5, W is 0.3. And in the future, we may consider varying the parameters and give the distribution of the parameters and adding the prime to these parameters. So this is our project. We can look at this noise image, this noise image, and this clean image. We can see that the processing as the noise is working. Okay, this have some code for your reference, and welcome to your questions and comments. Thank you.